I'm not hearing very well, but I think I can start, so I'll start. Um, Good afternoon, everyone. Thank you for being here. I'll present the paper Specification-Guided Repair of Arithmetic Errors in Dafny programs using LLMs. The authors are Valentina, Alexandre Mendes, and Alexandre Abreu, which is me. We're all part of the University of Porto, and Alexandra Mendes and I are part of the INESC lab as well. So it's probably no surprise to anyone there that software bugs are inevitable and they're very expensive to fix. And especially in safety critical systems, in which the assurance of correctness is a very important part of the development process. And in systems verified with formal methods, debugging can be sometimes harder because every fix must preserve the correctness, and also the complexity of the logic reasoning behind the program can sometimes even provide error messages that are difficult to understand. So automated program repair, or APR, aims to reduce this burden by generating patches automatically that will be able to help the developer to fix the problems they're having. So traditional APR tools validate fixes using test suites, but tests are incomplete. So a patch can pass all the tests but still be wrong or still not be the behavior expected. And that also provides the possibility for overfitting. And in contrast, formal specifications express the intended behavior precisely with structures like pre and post conditions. And they can serve as a much stronger oracle for verifying the correctness of the program. And our idea is to bring that strength into the APR process. So our main goal is to automatically repair arithmetic bugs in Dafny programs using their own formal specifications as the ground truth or oracle. And for that, we integrate three components. First of all, we have a file localization component using Hoare logic. Then we have pad generation using LLMs, and the verification using Dafny's own verifier process. So we use Hoare logic as the theoretical basis for reasoning about correctness. And just very quickly, if anyone is not used to it, a Hoare triple like PQR in that format means that P, the precondition P, if that holds before the execution of the command Q, then the postcondition R will hold afterward. So here we have an example where after the increment, the state or the postcondition is the change of the variable I is reflected in the postcondition. And by applying these rules, we can formally derive how each line of code transforms the program's logical state. There has been very few work related with almost the same goal. The main one is autofix, but it was made for AFL. And our idea is solving that problem in a different way. We want to use deterministic and non-deterministic components together to help with the APR process. So this is an overview for full pipeline. It's a lot, but we can delve into it. So we start with the Dafny programs, including its own specification. And we first localize the fault using Hoare logic and Dafny lemmas. We'll see how that works. Then we generate candidate fixes using one LLM, right, in a specific implementation. And then we insert the answer back into the program for re-verification. The cycle repeats until either a verified patch is found, so a patch that causes the program to be verified, or if all attempts fail. And for each suspicious line, we allow the LLM 3 attempts to fix it. So first of all, and this is an important part of the entire process, we assume that these specifications are correct. So there is a world where the specification is incorrect, and we are not dealing with that. We're dealing with the case where the fault is at the implementation. So first, we encode each of the logical entailments as a Dafny' lemma. So the pre-state becomes a requires clause, and the post-state, generally a post-condition, becomes the ensures. And then we ask Dafny verifier to prove it. If it fails, we mark all lines of that block as suspicious, and this gives us a list of potentially fault statements without the execution of the code itself. So here we have an example. This is a very simple code, absolute value of x, and we have an error at the second return, because instead of returning minus x when x is negative, we return x times 1. So we could calculate the states using Hoare logic, and the states indicate, for example, in case of the if else, inside the if we know the condition is true, in the else we know the condition is not true, so we can update the state using the rules. When we do a return, we also change the return variable if it exists. And for each exit point, we have to check the post conditions. So, for example, the second post condition is tested in the 2 exit points. So in each case, we want to know that this current state implies the post condition. The same thing would happen for the other post condition. And we can check them. In this case, if we checked this one, we would see that it does not hold, revealing that the line, the return line, is suspicious, the second return. So how does that look? In our tool, we first generate a lemma. So we have the current state as requires. So the state was x less than 0 and result is equals to x times 1. And then the ensures is the post condition itself. So in this case, Dafny would not be able to prove it. And once we have the suspicious lines, we can prompt an LLM to repair one of them. So each model receives a structured prompt, as can be seen in the upper image, with the buggy line marked by a comment, and is asked to return only the correct line. And for this example, we can also see an answer on the lower image, and a correct answer, which would be to change return minus x. So some information here is not included for brevity, but the important part is that in the answer of the LLM, you have the patch. So now we can take the patch indicated by the LLM and change the program. And then we can ask the Dafny verifier to say, does this pass the verification now or not? And that concludes the validation part. So the tool is implemented in C#, integrated with the Dafny verifier. You can communicate with local LLMs through LLM Studio or call APIs. And when a verified patch is found, we have the entire patch. So we have the location and the content, everything we need to change the program. So we considered many models to be implemented by our tool. And then we ended up choosing these 4 for their open sourceness, their popularity. And in case of Llama 7b, we wanted to test how a mathematical model would perform in this task, because it includes lots of logic, at least behind the scenes, right? So we evaluated it, and for evaluation we used Dafny bench, benchmark that was already cited before here in the Dafny'26. Includes more than 750 verified Dafny programs, including many real world ones. We split the dataset in 2. ground truth, which is the complete code, and hints removed, which is the code without the invariants and the assertions. We only use code that can be verified for these subsets, because the mutations that will create the bugs will be made by us, which are made with the 4 types of mutations. So we have operator replacement, coefficient modification, variable reordering, and any combination of those 3. And then we also indicate in the source which line was mutated for future reference. So here are the results of the full localization. We had very big success, close to 90%. But in some cases, the coverage for hints removed was around 60%. You can see on the histogram. And for ground truth, it was bigger, close to 80%. So that's the amount of lines that were marked as suspicious. In relation to the repair, GPT-4o Mini outperformed the other models, achieving, if you average both, 74% repair success. And Llama 7b performed very poorly, likely because it was tuned for mathematical reasoning rather than Dafny syntax or programming in general. So, but that was a test. So we can also see that 90%, 95% changes actually the fault line identified by marked in the source code, and that was the and over 80% reproduced the original fix. We can see the data for each one of the models as well in the graphs. And this is also very interesting. The attempts per success, we can see that we get diminishing returns. So if a model does not have a successful result on the first attempt, the second attempt will have even less chance of having one, and the third even less. So you can see it really clearly in the graph. And most for GPT-4o Mini, which had the best success, most of them were fixed already in the first attempt. So there are some limitations we can talk about and some discussion. So while the results are promising, we assume the specifications themselves to be correct, which we talked about before. So if the spec is wrong, so would be the repair. Like we're doing something that we don't want to. We currently only target arithmetic errors, and the performance depends a lot on prompt wording. Finally, and this is important to note, because some LLMs were trained using GitHub data, some Dafny examples from Dafny bench might have been used as a training data for them. So that could slightly inflate the success rate, although the input that we passed to the models were new because we added the mutations to them. So the errors, the faulty programs were new at least. To conclude, our next steps include supporting more bug types. As we said, we only deal with arithmetic ones for now. So control flow ones, for example, would be nice to have. We also want to explore more the repair of the specification itself. So if the specification is the cause of the fault, we want to be able to fix it and not the implementation. This could also be integrated in a VS Code plugin or any IDE, and that would help developers because they can have real-time feedback while they're programming of fixes they could make. And some key takeaways are the big localization success and the repair success, especially of GPT-4o Mini, which was close to 74%, and the integration of Dafny', Hoare logic, and LLMs for repair. Thank you all for your attention. I'll be happy to take questions. And just to finish, I'm part of this lab. If you want to know more about the work, you can access our website or look at the QR code. We have many projects using Dafny', so it's nice. It's interesting if you want. So thank you very much.
Do we have any questions? Okay, so yeah, I kind of having a side question. So your implementation, having an assumption that the specification is correct, and then the Hoare triples used to prove are correct, and you use it to localize your to use for localization. But I have a question that, aside from something like I'm from an Isabel Hall and Hall 4, and we do a lot of updates, and it breaks, and yes, that is one case then where this kind of thing gonna work. But I want to ask, like, is there a lot of other cases that is might work, because it seems to solve a very specific problem?
Sorry, at the end I got somewhat lost. I don't know it looked like to be breaking. I couldn't hear the end. Sorry.
Yeah. So
like at the end of the questions.
Okay. Is there lots of other cases aside from like Dafny' update or something like changing a very small thing in the proof? Is there other cases that this will work?